Welcome everyone, this is DW301 Basic Electronics, and now we shall continue our discussion on semiconductor physics. Before continuing the discussion, first let us recapitulate whatever we have discussed in the previous lecture. So, in the previous lecture, first we define the current density. What is current density? The if the cross section area are different, if somehow the cross section area are different, then a term current density is required. And there is a question for you now. What is the physical use and why okay, mathematically we define the current density is equal to I equal to ja, the current per unit area is the current density. But what is the use of, what is the physical use of the current density? So this is a question for you, and try to find out the answer. And in the subsequent lectures, uh, we will try to discuss the answer of this question. Okay, so first we define the current density, and with the help of integral, we excuse me, we try to understand the area. If the area is uniform, then directly we can put the formula, and if area is irregular and the shape is not uniform, then it means the shape is not well defined, then we will have to use the integral for the calculation of the area. As many of the people who have completed the plus 2 are aware of the area calculation, area and volume calculation with the help of integral. So this is an application of integral calculus, in which we can calculate the area of any random size and shape, and that can be achieved with the help of calculus. Okay, then we define the current density in terms of charge. What is total charge? Crosses the total charge crosses unit area is current density in unit time. This was just by some mathematical manipulation. Okay, and next we discussed about the uh, relationship between drift velocity and current density, and we qualitatively derive the relationship between drift velocity and current density. And one more way of deriving this expression, or you can say to achieve this expression, is given to you in the telegram channel, the notes about that, and that is just again some mathematical manipulation, and the definition of velocity and time etc are used, and that is for your self study. You can understand it. If there is any issue, then let me know, and then I will explain it again. And if you have understood this expression, and then that expression, and that way for deriving that expression will be easier for you. Okay, so okay, n into vd was the number of electrons per unit area, number of electron passed from per unit area in 1 second. 1 second. And if the unit area was not unity, then we will have to multiply by the term a here. A will also be here in the picture. Here we have taken a equal to 1 meter square. Actually, the simple thing is this. Again, I'm just concluding this all in one line. Basically, what is this? We are trying to calculate the number of electrons in a particular volume, and we know that in unit volume the number of electrons are n. It's just like a unitary problem. If something, some electron If there are 3 electrons in per meter cube, then how many electrons in 3 meter cube? Then 339. So by the unitary law you can understand, and this is very basic thing. Okay, so 3 into 3 9. So here we have just multiplied the to find the number of total electrons which are moving inside that particular volume. We try to use the unitary law, and by just multiplying the total area and the number of electrons in, sorry, by just multiplying the total volume and the number of electrons in per unit volume, means per meter cube or per centimeter cube. Okay, and this was the relationship J equal to minus Ne Vd, Vd equal to minus mu E, J equal to minus Ne mu E. So this was the relationship between current density and mobility of electron, and we discussed about the Ne mu. Ne mu was the conductivity, and we try to find out the dimension of this Ne mu, and we found that the Ne mu was the conductivity, and J equal to sigma E. J equal to sigma E is the Ohm's law. Again, with the help of one conductor, we excuse me. Again, with the help of some conductor J equal to sigma E, we tried to find the Ohm's law. So if we use the I equal to Ja, and then again we put the value of J equal to sigma E, and for the conductor by using some basic electrostatics, as the field applied was the E equal to V by L. V is the voltage applied and L is the length of the conductor, the field inside the conductor, and this is from the basic electrostatics. And finally we found that J equal to sigma E was the another form of the Ohm's law. Okay, and next there are few terms, G, conductance, and these the distinction between these terms must be very clear to you. G is the conductance. Conductance is the inverse of the resistance, and G equal to 1 by R, and R yeah, this you must remember, R equal to 1 by G, and okay, G equal to 1 by R, and conductivity and resistivity, and electric field, cross section area, length of the conductor, J equal to sigma E, Ohm's law, and this is the Ohm's law here, and sigma equal to Ne mu, Vd equal to minus mu E, and I equal to Ja, and here we have summarized all the formulae we have used up till now. And at the last point of the previous lecture, we were discussing some problem. If the temperature increases, how the resistance of a conductor will behave? Will it increase or decrease? Okay, now let us try to answer this question, and with this we will start today's lecture. Okay. So here the explanation is given. So what really happens whenever the temperature increases? Okay, excuse me, I should take a break.